Hi, everybody. Sorry for the short delay, and let's start. I will be talking today. I work at a company, and it will be awesome if some of you joined our team, or one of the teams that I'm responsible for, and that's the advertising. And also, of course, at StyleLounge.io, you can find a lot of information about what we do, what we work with, and what we look like when we drink alcohol. Let's start. I will be talking about patterns for reactive Node.js microservices. That means I won't be talking about what microservices are, why they make sense, what reactive. I will go a bit into the reactivity part, but not too much. And I also won't go into detail on why Node.js makes sense for reactive microservices. A lot of information about that is on the internet, and my goal was to kind of share more personal or more specific approach, insight to how we did things, and yeah, share some patterns that we found pretty useful. Let's start with what reactive microservices are before we go to the patterns part. Most of you heard about service-oriented architectures, and then afterwards came microservices. Service-oriented architectures sometimes are already message-driven, #enterprise service bus, and they usually have some kind of notion of decoupling to them. Some argue that if you do SOA right, you already end up with microservices because of the requirements to decoupling. Kind of the same thing holds for reactive microservices. Some argue that you can only decouple microservices properly if you make them reactive, but like everything, there's good arguments against that, and that's up for discussion, maybe tonight over a beer. Let's start with the term reactive. There's a thing called Reactive Manifesto. It's available at reactivemanifesto.org, and it postulates 4 properties of a system that a system has to comply to call itself reactive. The first is responsiveness. That means that the user or the consumer of that system always gets a response from the system in a very short period of time. And that's kind of the overarching property of such systems. The second property is that even if errors happen, the system has to stay responsive. So you might get an error response. Of course, we want to avoid that, but still you get it pretty quickly. The third property is again just a support for responsiveness. It has to stay responsive even under load. So elasticity is a requirement, and that doesn't mean, in my personal opinion, that it has to auto-scale from the first day, but it has to be built in a way that it's scalable by design and easy to scale as soon as that's needed, and then maybe in the future auto-scale. The fourth property is the only one that is postulated that says something on the inner workings of such a system. The Reactive Manifesto says a reactive system has to be message-driven. Of course, non-message-driven systems can also be responsive. They say, I agree to that, but again, that's a discussion outside the scope of today's talk. It's much easier to build reactive systems or highly responsive systems when working with message-driven architectures. So let's take a look at message and event-driven. I won't make a differentiation between the two in this talk. And there's different types. There's notifications. The basic idea is something happens, you publish a notification, some other system subscribes to that, and then can act upon it. But usually that's just a very small payload. Then there's event-carried state transfer. That means that everything a subscriber needs to action in an event is inside that event. So you don't have to have another synchronous operation to fetch data. The third one kind of is a superset again of the previous one. It's event sourcing. That could get many talks. It's an awesome thing. So I won't get into too much detail. The basic idea is that you store event logs, historized data that contain previous events, and then you can do all kinds of magic with that. But that's, again, outside the scope. The first one is not reactive, because if you get a notification, you have to fetch data from somewhere else. So there's synchronous communication involved, not reactive. The other one are. Let's take a look at something that's important to understand reactive architectures. which is a data flow chart. A data flow chart is pretty easy. It's boxes and arrows. I added the colors. And to explain what a data flow chart is, let's take a look at this. There's data making its way from the database to service D. And the arrows indicate how the data moves between those systems. So imagine A executes a read query to the database, meaning data makes its way to A. The arrow does not say something about who initiates it. It just tells you how the actual payload moves. Then we might have a polling relationship because B is polling A, and we might have a push notification going from B to C. I just tried to collect some. And a classic subscription where D subscribes to C. Again, the arrows only indicate how the data moves, and I just added the colors to make it more clear who's responsible for the relationship. Now, the first one is clearly not reactive because it's a synchronous operation to fetch something from a database. And polling is like something in between because, well, it's a synchronous way, or it's modeling asynchronicity with emulating asynchronicity with synchronous means. The other ones are clearly asynchronous and therefore allowed kind of in a reactive, or if a system communicates that way, it can call itself reactive. Let's take a look at a simplified example taken from the real world, to look at what advantages reactive communication in services has. We have here some services that we have in the real world. The product catalog somehow comes up with products. Maybe a good point to share 2 sentences about what we do. We are a price comparison for fashion. That means we pull in around 80 million products per day from our partners, various web shops like About You and others. And then we show that to the users so they can have the biggest assortment and they can compare prices. So it's a lot of data that moves through continuously, which is why we designed it near real time, reactive. So the product catalog somehow comes up with products, and then it publishes events like product deleted, product created, product updated, lifecycle events. Then the scoring subscribes to them to maintain its own local state. The same does the web app. It subscribes to those events and then maintains its own state, in this case Elasticsearch, because that makes sense for the web app. So data is heavily duplicated, and all those services only subscribe, and they only get data if something changes. In no other case do they get data. So that has some very interesting properties, and my favorite one is resilience, because if now the product catalog completely crashes, the scoring will still continue to work. And not only that, if there's tracking events generated in the web app, then they are push notified to the tracking, and then the scoring still subscribes to, of course, because everything's working there, still gets updated tracking events. So if users use the site and we have some kind of score that takes into account what people actually like, that still works even if the product catalog service doesn't work, because those updates still flow. Of course, the scoring and the web app don't get events from the product catalog, so the inventory might be outdated, but what's there has accurate scores. If the tracking dies as well, of course, we don't have up-to-date scores, but if the developers decide, yeah, well, whatever, it's dead anyway, let's rather create a new feature in the scoring, and they deploy a new scoring strategy that calculates another kind of score, and they deploy that, then the scoring will still be able to rescore the products it knows with the tracking data it knows, publish that, the web app subscribes to that, and the new score still ends up on the web app. So this helps a lot when decoupling what people do on the system. And yeah, it's kind of the optimal case in terms of resilience if parts of the system crash. And you don't need any boilerplate for that. That's just an inherent property of message-driven systems. If the scoring dies, of course, there's no new data coming into the web app, but it still works. And that's a completely different situation than with HTTP microservices. If you have one service in front and then some behind that, and the ones behind that are required to serve a request, and they die, there's no way on serving that request to the user. So that's a conceptual advantage. Of course, you can work around that with caches, but I like it. Another property is, of course, if you just subscribe to events, it's pretty easy to scale, because If there's more users hitting the web app, you don't necessarily have more products, so you don't have to scale the product catalog. So errors don't cascade outside the system towards the user, and load doesn't cascade inside the system from the users, so you don't have to load balance everything. Okay, so in short, data is heavily duplicated. Things are very decoupled. If somebody worked with DDD or is working with DDT, it's also interesting to note that as each service has its own domain model, they have their own model, they have their own bounded context, and therefore it's rather easy to model in this situation. You have to think about what's talking or what's subscribing to what, but not necessarily on how can we come up with a data model that serves all the needs or something. So in practice, we think a lot about flow, but we don't think about data models, which is fun. So we did that. We started with that about bit less than 2 years ago, and we have a lot of stuff running by now. Of course, this at some point only works with continuous integration and Docker and Kubernetes. And yeah, that's it. Let's start with the patterns. And what are patterns? I'm not talking about design patterns, but I have a much more fuzzy approach to patterns in this talk. It's reusable things that kind of allow talking about, or reusable, yeah, let's just show that. The basic idea is that you can talk about them, that you can share them, that you can discuss applicability, which is the most important thing. With just a framework or rules or whatever, it's much harder to decide, does it make sense? So it's very small atomic structures for code, behavior, architecture, design, and so on, that you can basically discuss, does it make sense here? And do we have a new pattern or stuff like that? So it allows a very sophisticated discussion. I won't be talking about some things that I consider basics, even if they don't apply to everything. I would say in general, for example, having read what a 12 factor application is and using some of the best practices and patterns out of that makes sense. Continuous integration, of course, makes sense in microservices, in reactive microservices, in any kind of decoupled system. Testing is awesome. Testing is somehow still underestimated in parts of IT management and parts of IT in general, but it's super important. Same goes for linting to sustain consistency. Let's start. The first one, and of course, playing with new cool technology, that's also something we had to learn, is know your weaknesses. With reactive microservices, some problems you just don't have. We don't have scalability issues, and we don't have those big ball of mud issues. And those are, in my experience at least, the overwhelming problems that you have in software development. On the other hand, you have eventual consistency, which is awesome if you master it, but it takes some time to master it as a team and to really understand what's happening under the hood. And for that, you need powerful monitoring. So what I want to get here at, there's no silver bullets. It's really important to understand what technologies, paradigms, and languages can be used for and where their weaknesses are. That doesn't mean necessarily immediately switching the stack when something new comes out, but still understanding what's wrong or not as good about what you work with helps a lot in everyday decisions. Yeah, of course, that being said, some things are better for specific domains than others. So I'm not voting for nihilism or relativism. It's just some critical rationalism. A lot of isms. Next one, the walking skeleton. Of course, we also had to learn that the hard way. Most of the unexpected scope creep or unexpected additional work from inside the IoT came from the integration phase of issues, of user stories. So everything is kind of done working on our own machine, and then it starts to get nasty. And the only solution for that is basically to turn the horse around. That's not really a saying, but you know what I mean. To start with the integration part and then afterwards implement the actual feature. And that usually works because then you know that it's working with the infrastructure, and it also forces, or it forces us a lot to design for failure. Like if you put crap mock data into your production or staging system and then find a way to clean that up. That usually means that there's something right about the software. Canonical names. Sorry for this, the big amount of boxes here. What we have here is 4 components, each consisting of microservices communicating asynchronously. And probably all of you know projects where things are, I don't know, named like Zebra, and then that's a recursive acronym for something that somebody found funny. And most of the times those things are funny, special names for things, animals, people, whatever. The problem is it's really hard if you're the second or the third developer in that project to get what's really going on. And especially if you want to scale your team quickly, that gets really nasty. So what we found really useful is, in this case, for example, you have in the scoring service, you have a scoring product persister. That means it's a part of the scoring service, and what it does, it subscribes to product events and it persists them. It's not really creative, but it really describes what it does. Same for the scoring tracking persister. And then we have a scoring tracking database and the scoring product database. It's pretty clear by now what they actually do and what's in there. Same holds, of course, for the other services. We have the mailing product persister. And just by looking at these, I think everybody can pretty much come up with what they are actually doing. Not all of them, of course. There's different use cases and different components. But using some consistent wording, like in DDD, to name components, but also use parts of words to name components, makes it really, really easy if you have a lot of microservices to really understand what's going on. And these need a lot of iteration, a lot of renamings, and that's also something that's, in my opinion, important to not be afraid of. The next thing is kind of builds on that, and of course you don't have only names for individual services, you also have different countries that you might deploy to. You might cluster stuff, you might put stuff on staging and in production. So, and this is just an example, this is not a guideline or something. This is what works for us, and that is completely different for each domain. So here we, for example, have 5 scoring persisters running on staging Germany, and then this one scoring calculator that subscribes to their events. It's pretty straightforward. And same, of course, for the others. And what makes it even easier if you put these into domain names, because then you have addressability, and just by thinking about what a part of the system is doing, you can already come up with a name, or at least have an educated guess. And that makes it so much easier for onboarding people, especially if you have, like we do, 70 or 80 microservices. So this holds for small startups with many microservices, big companies with many microservices, and big companies with only a few components, because then again, it's still big. Okay, next one. And sorry for this brain dumpy attitude. I think, yeah, why not more content if we have the time? Values over objects. I don't know, who knows Rich Hickey? Cool. He's awesome. There's some awesome YouTube talks from him. I kind of copied everything I say on the next 2 slides from him. From JavaScript, you probably know those 2, and the left one is classic classes, like in Java or other OOP languages. The right one is an ad hoc data structure. The right one is a value, and values have a lot of advantages. Working only with values instead of entity classes allows you to easily fabricate them for unit tests, for any kind of other tests, integration tests. Any test that you do with your system. They are fully language independent, which again helps a lot when you're doing microservices. And they can be immutable. They don't have to be, but you can treat them immutable. If they're actual values, they should be immutable. And yeah, probably at least the JavaScript developers love that concept. And even better, they aggregate to values. So it's much easier to work with them, and you have little to no boilerplate code, because you're just expressing what you're doing. Of course, they have some disadvantages. I will come to that in a minute. But first, let's add a second pattern and then combine them. The second pattern is validating first. All of you know that. Turns out to be pretty awesome to just validate everything early, because then you have the trust that what you're working with makes sense. and you have some kind of protection during runtime, whereas classes, for example, provide structural protection during during compile time. Also, you need less unit tests in some cases. Where I actually want to go at is this one, because you can combine the two in a pretty awesome way. As I said, objects and classes in OOP provide some kind of structural safety. If you have a class car, you always know it will have a string if the property driver name is defined as a string. So they provide structural safety. Actually, the same thing can be done, for example, in JavaScript, but many new languages support this kind of approach by combining interfaces, as they're called in TypeScript, let's call them structural interfaces for now, with schema validation, because then you can define the structure of your data, and then during compile time you have structural safety, and during runtime you have the safety from the schemas. And schemas are much better at providing structural safety than classes are, because they're purpose-built. You can assert much more, and you have a very clean, declarative, reusable way of doing that. So this is a pretty awesome combination. Errors. This is a function, and what does it do? It tries to get data from a database, and it tries that up to 5 times before it crashes. This is just some code to fit on the slide. In many systems, those things are much, much bigger. And the only reasoning behind this is that it shouldn't crash immediately. So what I colored is actually the only business logic, so to say. So if you embrace crashing, then it's much less code, of course, because it's just one function that does a query. The problem with this is it immediately crashes. That actually has a lot of advantages, because then the application, again, is in a clean state. The application, again, is in a clean state, and nothing can go wrong. If you look at this code, where we actually introspect an error, that can be really dangerous in practice, and lots of things can go wrong there. So if somehow possible, embrace crashing. That can happen in traditional microservices with heavy load balancing. That can, of course, happen without any boilerplate in reactive microservices, because if a reactive service dies, it just restarts and gets the same message again. And then again, we are in a clean state. And that makes reasoning about such a system much, much easier, because there's close to 0 try-catch blocks in the code. Another example where try-catch can be dangerous. This is a typical situation. We're trying to do something, and we don't really care what went wrong, so we return some default value and maybe add something to the log, because you never know. Problem with that is if somebody refactors the query function without knowing the first code of block where it's used, by, for example, adding a cache, then it gets dangerous, because if this cache has state and it crashes, then it's not functional, but we're not throwing through here. So what happens? The application is in some kind of a zombie state. Parts of it are actually not working anymore, but it's still running. And in those situations, all kinds of things start to go wrong, and it's really, really hard to chase after bugs that happen in such a situation. And if there's important data involved that is then being corrupted, that sucks, basically. So, pattern that we found pretty useful is never catching generic errors. It's kind of okay. I mean, sometimes catching is required, especially when working with libraries. And then being really strict about this is not super strict, but being relatively strict about what is an acceptable error condition makes the system much, much cleaner. Okay, reuse, one of my favorite ones. Don't repeat yourself is basically what IT is built upon and what the world is built upon, and it's an awesome thing, but it has some disadvantages. Basically, every time we're extracting code, we're like reusing a function somewhere. We couple the two instances where we use that function together, which is super okay. It's just something to have in mind, because in my personal experience, people drastically overestimate the time savings from extracting code and underestimate the maintainability issues that come with that. Because usually we're thinking about, yeah, let's write it and then it's done, but actually the the big part of the life cycle of software is maintaining it and not writing it. So I don't know, who here has written a framework that nobody uses? Okay, cool. Maybe it's actually more hands, I don't know. But that's a common thing. People love writing frameworks, and people love writing externalizing code. It's a great thing, it's just dangerous. And of course, the same holds, of course, for copy-paste. So if the result is, instead of externalizing, just copying something, it's as dangerous, basically. And a takeaway that I really like about this pattern is that coding is very little about the actual code. Rewriting a system that you wrote is super easy, or usually super easy. It's more about understanding a problem, and externalizing stuff and fixing a structure does not help a lot often about understanding a problem. And of course, the frameworks. Frameworks lock in the current state of domain knowledge. It makes sense to use frameworks in many situations, but writing them usually doesn't. And maintainability is not necessarily the same thing as brevity. It's cool to have short code, short functions that do something, but in the end, at least if it's for production, at least if somebody's paying us for it, in my opinion, maintainability is much more important, especially if you're the new guy in the team and you have to deal with what the others did. So yeah, I said that before, so let's skip that and talk about migration. This is actually about reactivity, because it's of course cool to talk about reactive microservices and how they work and stuff, but how to get there. What we found pretty useful is a reactive facade. It's a legacy. We have a legacy microservice with a database that could be a much bigger system actually, and we want to add a reactive service just because we want to play around with it, learn does it make sense for us. What we build is a publisher that is triggered by cron or domain events and scans through tables, for example, and compares them with a small cache to calculate deltas and then publish those, like product created, product updated, product deleted. And then service A can subscribe to that in a fully reactive fashion. Then you can add more services and more services and more services, and at some point add a legacy persister. And again, this is the naming that we used before. This legacy persister subscribes to those events and maintains data inside a table inside the legacy system. And that way, you can very well interface the two worlds. Helps us a lot. One of them is still functional because there's still some legacy code, of course. Some meta stuff. The first one, we had to learn that the hard way. Not unit, I just read what's on the slide. Monitoring is really, really important in dynamic systems, and reactive microservices are highly dynamic. Basically, unit tests protect during deploy time, and the same holds for logging, metering, alerting, and what we found really useful, frequent automated consistency probing. We have some components that check other components to ask them, like, how many products do you have from this shop, or how many products do you have per category, compare them, and then be able to extract metrics and create alerts. That's super simple. That's just basically queries to endpoints that you have to send out, and they have to support it. And then you have cross-system consistency checks in a reactive system, in a potentially, or almost all of the case, eventually consistent system. So we even started to create metrics before we create the application, which is kind of the architecture equivalent to TDD. And last one, of course, collect patterns. Probably some of you think, okay, not everything in this talk is really a pattern, in my opinion. We broadened the term in order to have a meaningful conversation inside our IT department to talk about structures and to transfer knowledge. Thank you.
So, Alex, thank you. It was a pretty intense talk, and I think I didn't understand very much, but that's not because of the talk. It's just because I'm not really deep into Node.js and these patterns. So that's why I hope there are some questions around here. Can you check the app if there's some question? Oh yeah, no network. So is there someone who has a question? Yeah, great.
Thanks for the talk. It's very interesting. I am questioning, I mean, microservices are great, maybe also because they are stateless or like behaving pure. And now we are reintroducing state. And I would like to know how can the microservice catch up with the state when it starts? Do you have databases employed or caches like Redis? I don't know.
The cold start problem, favorite one. Yes. Let me just check if I can get to. Yeah, whatever. So you said pureness, and that's an important term. Our favorite services are the ones without state, of course. They scale like hell, and everything's easy. We tackle the cold start problem by telling the service further up the stream, kind of. We look at like upstream, downstream, and we tell the service further up the stream, the publisher, to republish its entire state. And that's it. Yeah, no, that's basically it, yeah.
And how do you keep the state? Are you using Redis or just plain RAM?
Usually, no, not RAM, because we want to have a crash-only design. But all kinds of databases. We have Redises, we have React KV, not anymore because they're bankrupt, but we used to have a lot of React KV, MongoDB, of course, some BigQuery, Elasticsearch, Neo4j, InfluxDB, MySQL, PostgreSQL, really depending on the situation. I mean, the cool thing about microservices is you don't really think about you think about what database to use, but you don't think about implications for the broader system because it just doesn't matter.
Thank you.
Any other question? Yeah, cool.
Thanks. So thanks for the talk. It was very interesting. One question I have is regarding basically managing the interfaces between the microservices. So from my experience, I know that in bigger teams with multiple interfaces, it's hard to, change, for example, existing interfaces because you never know who's using it or how it depends on other services. So is it just internal documentation you do, or is basically the validation schema at some central place? How do you manage that?
It's of course not central, so that everything is decoupled. Even each component has its own message broker, so everything is fully decoupled. What we do is we have per component a small domain repository containing interfaces, schemas, mock objects, stuff like that to work with. And we have, just like an AP blueprint, but our custom version of that for reactivity, we extract information about publish and subscribe relationships from the README files inside the repository and then have a browsable architecture experience, we call it. And there you basically see those relationships. How do we manage changing interfaces? Right now, it's really easy because we just deploy the new thing and then downstream the services crash and then we deploy them too. And if it takes half an hour, that's okay. So there's no, we have versioning in the system, but we're not using it right now because it adds too much complexity. That really depends on the system, so on the situation. So default case is versioning, just like in traditional microservices. We take a shortcut by just deploying that, and then it fails because of the schema validation, and then we deploy it, and then it's fine. Rolling back and deploying is super easy in such a system, and it doesn't hurt because you don't have any downtimes, because, yeah, it's asynchronous. Yeah.
Cool. Any other question around here? No? I think my question would be more like top level, not so deep, but anyhow, I have one question. How many fights did you fight between PHP and Node.js, for example?
That's a good question. 0, basically, because when I started, the first thing was to introduce Scrum and to kind of set up the basics, pair programming, pull requests, stuff like that. And at some point, you start a conversation, and people want to play around with stuff. So at first we had some reactive PHP microservices because people were sure that PHP is the better tool. But the cool thing is you can just let them do it. And then after a while, people just stopped touching PHP at all. And I mean, PHP 7 is a bit more advanced, so there's some pretty cool things you can do with it. Node.js is smaller, and in my opinion, just because of the interface, is better suited for the job. But in the end, let people play, but do it in a way that there's no big decisions, no big impact that has.
Okay.
Yeah.
So that would be another question. Did you evaluate something else at the beginning, or did you start right now in Node.js, but you said you were using PHP as well?
Yeah, we were PHP only in the beginning. We evaluated a lot, but we never made big decisions. So we never came up, let's do reactive microservices. The first idea was that we rewrite the whole system using Symfony instead of another PHP framework. That was a very bad idea, and we got protected from it because funding didn't happen, and then we had to let go some freelancers, how it is in a startup, and then we had to rethink the whole thing. And then we started writing small services for small solutions, and we basically started implementing new features using tiny Node.js microservices. And that really saved us, because then after a while, first we did it with scoring, and then after a while, we said, okay, why not also do it with a web app? Why not subscribe? And we kind of sold it to ourselves as some advanced caching. That's basically it. And then we saw, okay, it's working, and then you start kind of building more and more with that. So, yeah, we didn't know when we started.
Okay. Yeah, cool. Oh, there's a question. Yeah, I don't think if we have enough time until I'm at... No.
Yeah, we have 6 more minutes, that's fine.
Yeah, no. Was just a joke because far behind.
Yeah. Mm-hmm. I would say if you have to change something, if your change affects so many things, then the coupling is too tight. If you look at validation, for example, the only point where multiple repositories share the same validation logic is if they subscribe to the same data, and then inherently you have to touch it. So there's no way around that. We have a very strict rule that no service must use data it gets internally. So they can use it to validate, but then they have to map it to their own domain model, which with plain objects is super easy. But they have to do that because if you start just persisting stuff that you get in the same structure into the database, it's a nightmare. You can't really refactor that. You can never get out of it, or it's really hard to get out of that again. So if you have clear boundaries between the services and then the service takes over, has its own responsibility, then I would say you're protected against that. But of course, we're 13 people in IT, so that's just a feeling.
Yeah. Is there some other question? Yeah.
Thanks. Well, so my question would be, you had one slide showing that it's important to validate the data early, so you know what you're getting. So I was wondering, since you have that many microservices and that many kinds of events, you probably have some kind of event schema. How do you manage and share those schema? And how do you get the microservices to evaluate the right schema?
Let's assume we have a publisher and a subscriber. The publisher holds the schema for everything that it publishes. It is responsible that that is consistent. And if we would want, we didn't do that yet, but we could also have outgoing validation. We didn't need it yet because we detect it further down anyway, but that's something we could do. And then the subscriber basically pulls in that domain package from the publisher via NPM, and then has access to the schemas, and then it can validate that. So if something changes, we have that visible through semantic versioning. and then the subscriber can afterwards map it to its own domain, and then we're safe again. Yeah. So what happens if we change something? Usually downstream the services die, and then we can redeploy them, and then it's fine again. Yeah, or we can also pause execution. Usually we're just too lazy and let them die because whatever, it's just containers. But we could also pause execution. Yeah, on staging, of course, most of the time.
Oh, okay. Oh, there are a lot of questions. I think we will take. Do we have time? Or? So otherwise, we take one question and then we or the two.
In case of server-side rendering, do you provide synchronous GET API as well, and GET endpoint?
I don't know, because right now we're still stuck with Laravel. We're currently migrating that to React Redux and have some pretty awesome guys on board for that. But right now we only did part of it. So the web app thing is a component, meaning it consists of microservices. It has some persisters, caches, Elasticsearch, stuff like that. We don't know yet how to apply reactivity to communication between client and server. We know that it will be a universal app. I don't know. If you have some idea, let's talk about it later.
So there was one other question? Yeah. No, it's okay. I think we can do it.
Yeah, you mentioned very few programming languages, basically PHP and node.js.
Yes.
But I stopped counting after 10 different database systems. So how do you handle that from an operations point of view? Because each of them has different take on replication and incremental backups and so on.
We back up very little inside the system. So we have some single sources of truth for tracking and the feeds from our partners, for example, that stuff. But if something that is downstream and is basically a function of that data dies, we can just re-emit and we're good. So most of the databases we have, we don't really have to care for them. If they die, it's just a few hours of refilling. That being said, for the others, of course, it's more important. Luckily, the feeds we have as files, and the tracking data we have in BigQuery, so there's no ops involved there, or close to no ops involved there. And how do we manage the setting them up? It's basically Docker and Kubernetes, and we have a thin layer around Kubernetes that allows us to write shorter files and maintain canonical names inside Kubernetes files. It's kind of a preprocessor, and therefore, it's super easy, basically. So it's nothing we think about a lot. I mean, we think a lot about what database should we use, and it's an ongoing joke that we're just using a database because we didn't use it yet. But yeah, it's not really a hassle.
All right, then thanks, Alex, for the talk, and thanks for the questions, and again, a big applause.
Thank you.